In this paper, we present EnvyDepth, an interface for recovering local illumination from a single high dynamic range environment map. In EnvyDepth, artists quickly mark with strokes the regions of the environment map that should be grouped together. From these annotated strokes, EnvyDepth uses edit propagation to assign a depth to each region and create a detailed dense set of virtual point lights that reproduce both the local and the distant lighting effects in the original scene. When compared to the use of distant illumination only, the added local information better reproduces a variety of local effects such as shadows, highlights, and caustics. EnvyDepth annotations take only tens of seconds to produce plausible lighting without visible artifacts, even for complex scenes, both indoors and outdoors. The generated lighting environment work well in a production pipeline, since they are efficient to render with, and they can be easily controlled for artistic purposes via the interface. This is an example of the workflow of EnvyDepth in the case of an outdoor scene. For each edit, the user selects regions of the environment map that should be reconstructed together using a sketch-based metaphor. Two types of strokes are placed directly on the environment map to indicate regions that should be included or excluded from the selection. Edit propagation is then used to compute the selection from these imprecise strokes. Then, the user assigns a geometric primitive for each selection. EnvyDepth supports three basic primitives. The first is represented by horizontal or vertical planes. This primitive is perfect to represent the floor, the ceiling, or elements that are not in the close proximity of the probe position, like the buildings in this case. The second primitive is represented by extruded planes. They are generated starting from the boundaries of areas which are already assigned to a plane. This primitive is perfect for indoor environments or squares. Elements which are not straight, like the walls in the room of the previous example, can be easily reproduced. The third primitive describes the distant illumination. It includes the sky dome, but also objects that the artist feels are far away enough from the rendered object. The primitives are then converted in a set of virtual point lights. Virtual point lights are a flexible representation of the lighting environment, which is supported both by scalable offline rendering algorithms and their interactive counterparts. Results show that the estimated local information better reproduces a variety of local effects, such as shadows, highlights, and caustics. Comparison with state-of-the-art methods show that the accurate results can be achieved without the need of acquisition devices or time-consuming manual modeling sessions.